All right. So after watching the video, in this subject, the study of statics and rigid bodies, which is the equilibrium of a particle, and currently in two dimensions, is fundamentally about the balance of forces acting upon it. So for a particle to be in equilibrium, the vector sum of all external forces must always equal to zero. So this can be expressed through the equation summation of Fx is equals to zero, or the summation of all forces acting on the x-axis is equal to zero, and also for the summation of Fy is equal to zero, or the summation of all forces acting on the y-axis is equal to zero, where f of x and f of y represent the horizontal and vertical components of the forces, as I have said. So if these conditions are satisfied, the particle will either remain at rest or move at a constant velocity, illustrating the principle of inertia in a static. Well, so in application of previous discussions, previous lessons, force vectors play a crucial role in analyzing the equilibrium. So each force can be represented as a vector with both magnitude and direction, and with multiple forces acting on a particle, they can be resolved with into their respective components by employing vector addition, so I can visually and mathematically determine how these forces interact. So for example, when the forces are could become coplanar, meaning that they lie in the same plane. So with this simplification, it allows for easier calculations and graphical representation using methods such as force diagrams. So with these diagrams, it would help me visualize the equilibrium state by clearly showing how these forces balance each other out. So furthermore, the concept of with the said coplanarity is essential in practical applications, such as in this subject, where multiple forces act on a object within a defined plane. So, and also in relation to static equilibrium analysis, that would ensure all forces are coplanar allows for straightforward application of static equilibrium equations. So, with this understanding, it would not only help me for theoretical study of mechanics, but maybe in real world applications, right? So how do we, so now in this solving of the equilibrium of a particle. So the first step is to identify the given problem or the given diagram. So I start by identifying all the forces acting on the particle. So this would include gravitational forces, the tension on the um, tension, the normal forces, maybe friction, or any applied forces. And also next is to create a free body diagram to visually represent these forces, labeling their magnitudes and directions. So with the free body diagram, it would serve as a crucial reference for later calculations and would help me visualize how the forces interact. So now next is to resolve the force into the x and y components. So once the forces are represented on the diagrams, we resolve them into their horizontal and vertical components. So we use trigonometric functions to break down forces that are not aligned with the axis. Or for example, if the given force acts at an angle, well, its components can be found using um, multiplication of the force or cosine multiplied by cosine if it acts on the x-axis and multiply it by sine, function of sine, if its force is acting on the y-axis. So now next is the application of equilibrium conditions as I have said the earlier formula. So with the forces resolved into components, we can now apply the equilibrium conditions. So we set up the equations based on the requirement that the sum of the forces in the both x-axis and y-axis must equal to zero. So this will give me a system of equations that I can solve simultaneously to find unknown forces or the value of their parameters. While if additional constraints are present, such as angles or magnitude of certain forces, we can just incorporate those into my equations. So once solved, it would ensure me that the results satisfy the equilibrium conditions to confirm that the particle is indeed in the state of equilibrium. Hello. So I have here four examples of a problem. for sample problems in the equilibrium of a particle. So I have here four problems, one, two, three, and four. So let's start by solving the first easy one. So we have here the given mass of 10 kilogram and our angle right here from point A to point B. And now the problem is we're looking to find the forces acting on point AB to point AC. So first we need to analyze the diagram and to make it easier for us to determine and analyze, have to make a free body diagram. So just going to do the same. Oops. Your mass is going to be the angle. We have a given of 30 degrees of angle. There. This is point A, point C, point B. And our mass right here is 10 kilograms. But we cannot use this unit, this number with our solving. So we're gonna have to transform it into its weight. So we have 10 kilograms. We multiply it by the gravity, which is 9.81 meters per second squared. And that would result to 998.1 newtons. Okay, so find the AC, find the force acting on the point AB and point AC. You can use the two formulas. We have the summation of xfx is equal to 0 for the summation of forces acting on the y-axis is equal to 0. But before I further proceed with the calculations, I need first to analyze which one of the two formulas can be used. So we need to use the second formula because using the first formula is not complete. We only have one given, which is we only have one force acting on the x-axis, which is 30. So we're gonna move on with using the formula for summation of Fy is equal to 0. So what we have now is first we have the 98.1. So we're just gonna have to summation of Fy to we add all the forces acting on the y-axis. So we have here going from point A to point B, there is a TAB. The forces acting on y-axis from point A to point B, we have TAB. We're gonna use the sine, and 30 degrees. And minus, because we're gonna put minus sign because the 98.1 is on the negative side of the y-axis. So 98.1 Newton. And now to actually get the TAB, because we can further proceed with the calculations. So we transpose the sign, remove the TAB. TAB that will be equal to 98 point, wait, 81. Oh, 98.1 Newton. We, oh, we forgot to put the to sine 30. TAB sine 30. So notice that we can't actually solve this one. So we divide both sides by sine 30. So we're now left with the TAB, which equals to 98.1 Newton over sine 30. So you put that into your calculator, and I have a result here of 196.2 newtons, or 196. 196. So that's for our TAB. We have now our first equation that we can use. So moving on, after we've done with this second formula, we can now use the first formula, summation of fx. Summation of fx equals to 0. So now we can input, so TAB is cosine 30, cosine 30 minus TAB. Yes, right. Okay, so now by transposing, so notice that we have here the value for the forces acting on the point from point A to point B. So we're gonna have to insert that. So TAB is equals to 196, right? 196 Newton cos cosine 30 minus 3AC. So now we can now find the value for 3AC by transposing it on the other side. So we're gonna have forces acting on the point A to point C is equals to 196 cosine 30. And that will give us the answer of 100, 170 seconds. And there you have it for the problem number 1. TAB is 196. And the forces acting on from point A to point C is 170. Right. Done with the first item. Moving on to the second number, the problem that we have. On to the second problem. Here with the given dimensions we have. So also with the mass given. So let us convert this into it first. So 100 kilograms is equals to 981 newtons. Right. So notice that we have the dimensions given. But first, let me do the free body diagram to make our life much more easier. Okay. Oops. For the 981. So now on the point A to point B, we have here given angle of 50. So using the same equation of the summation of fx and the summation of fy, we need to first integrate the vertical and the horizontal components on each side. But notice that we have a given dimension. So we have 4 meters, and here we have 3 meters. Point A, point C. So this problem is actually the same as the previous one. So moving on into integrating the vertical components, we first on the what is acting on from point A to point C. So we have the given dimensions, but we don't have the angle. So what we can do is find the slope of this force vector. So notice that the 4 is parallel to the x-axis. So we're gonna isolate the triangle and invert this triangle. So we have here 4 on the adjacent side. We have 3 on the opposite side. And if you want to find the hypotenuse, you're gonna have to do the Pythagorean theorem. Just C is equals to the hypotenuse equals the square root of a squared plus b squared, and minus. Right. So the hypotenuse is equals the square root of square root of a, which is the opposite side. It's 3 squared plus b, which is the adjacent, was squared. So in the algebra, we have, simplifying it, we have 9 plus 16. So it means square root of 25, and that will be 5. We'll put in here 5. So we have hypotenuse is 5, adjacent is 4, and the opposite side will be 3. So now we can integrate these forces acting on from point A to point C. So for the x-axis, we have, so actually we're gonna have to use the SOHCAHTOA. So, TOA. So since we have to find the x forces acting on the x-axis, so we're gonna have to use the cosine first. So that will be FAC multiplied by adjacent, that will be 4 over hypotenuse, that will be 5. So this one's acting on x-axis. And for the y-axis, that will be the opposite over hypotenuse. So 3 over 5 acting on the y-axis. And from this one is acting on FAC. So our force is acting on the from point A to point B. We integrate those forces. So I'm going to use for the x sine, then cosine, sine 50 for the x. And for the y-axis, I'll be sine 50. So now we can now move forward with the adding summation of forces. Uh, for the summation of fx, we have forces right here. SAC, let's see, from point C, there's 4 or 5 plus this one on acting force AB. Force is acting from point A to point B. There will be cosine, oops, cosine this. And now you do the math. Right, so I may have made a mistake. So this one is not positive at all because forces on the x-axis from point A to point B is on the negative side. So this will be minus. So of course AC do the math and you do the math and you have 0.8 minus. So FAB, the cosine of 50 is 0.6248. Right. So now we have to transpose. So we're gonna have to find for the value of FAB first. So if we have negative FAB, 0.248 plus SAC, point, is equals to 0. Can now multiply, can now multiply this by a negative. That will be the sign negative as well. But when we transpose, we're gonna have it back to positive again. So that will be FAB 0.6248 is equals to FAC. Now we divide both sides by 0.6248. And now you have a value of roughly 1,245 FA. So whatever the value is, so actually, whatever the value for this FAC, we're actually multiplying it by 1,245. And that would mean that this one will be your first equation. So we're done with the summation of f of x. So moving on to the summation of all forces acting on the y-axis equals to 0. Putting all the ingredients, we have this one and this one. So the SIB, oops, we have the SAB, that is sine 50. plus the FAC, and its value is 3 over 5. So this one isn't the only forces acting on the y-axis. We do actually have here the 981 newton, but this one is on the negative side of the y-axis. So it will be minus 981. So we simplify things first. Maybe sine 50, that would equals to sine 50, that would equal to 0.77, I mean 6. 766 plus the FAC 0.5, that is 0.6. And since we're looking for the forces, then we have to separate these unit right here. So we're gonna have to transpose that, moving out outside the equation. 181. Right. So notice that from the first equation that we have here, the value of FAB is 1,245. And we're just gonna plug it in. 1245 multiplied by 0.766 plus FAC. AC 0.06 is equals to 81. So now we have here 1, 5, solve this, 0.554 from multiplying 1,245 to 0.766 FAC equals to 981. And now we divide both sides by 100, 1,500. I mean 1.554, 5.5, and the value for FAC will be 131. Problem here, I've answered. Going back on our first equation, we don't have an absolute value for the FAB since the value of, since now we have the value of FAC, so we multiply 1.245 multiplied by the given 631, and now we have an answer of FAB is equals to 780. So this will be your forces. So forces acting from point AC is 631 newtons. The forces acting on from point A, point B is 786 newtons. Right, so moving on to the third problem. So notice that from point A to point B, the spring has a stretch length of 0.5 meters. So now we have to find the MD for the mass of the point D. So we go by usual by drawing the free body diagram. But notice that we have another dimension. So dimensions given. So this will be 4 meters. And this is 1.5 meters. Going to be a point C, point A, point B. Another dimensions here, we have 2. So constant strain of acting on point A or point B is 100 kilonewtons a meter. Right. And on constant strain, we have from point A to point C that is 50 kilonewtons a meter. That's here. And we find the mass for this point D. So I'm going to draw that again to move forward with the dimension of the um, triangle. So from point A to point B, we're going to invert the triangle. So we have a given 2 meters that is parallel to the x-axis, to and another parallel to the point mean to the adjacent. And you plug it in your Pythagorean's formula, and you'll have a result of 2.5. So we just determined the total length of spring referring from point A to point B, 2.5. And we do it on the other side. We have 3 meters, 1.5. Place this 1.3. And do the Pythagorean's formula again, you have a result of 3.354. Right. So doing the spring formula, in order to find the forces acting on from point A to point B, you're gonna want to find constant spring multiplied by the stretch distance spring. So now, in order to find the stretch distance of from point A to point B, you're just gonna minus the current current length of the spring minus the unstretched length of the spring. So we have here the unstretched value that is zero point 0.5, and the current length of the spring is 2.5. So 2.5 minus zero point 0.5 meters. That will be the stretch plane is equals to 2 meters. So now we have the value of KB, of course, the constant spring, of course, acting on the stretch spring is 100 kilonewton over meter. So find AB, force acting on the spring from point A to point B. We now have a value of 100 kilonewton per meter multiplied by the stretch spring, that is 2 meter. And forces acting on the spring from point A to point B is 100 kilonewtons. Oops. So we're gonna move forward by using the formulas for the equilibrium of a particle. So the f of x is equal to 0. Therefore, we get all the forces that acting on the x-axis. So we have from the FAC, I'll just write it down here, FAC, that is negative since this one is going on to the negative side, maybe the positive side. Negative 3 meters over the hypotenuse, since we have solved it earlier, is 3.354. 3.354. And on the FAC, which is acting on the FAB on x-axis, that is 2 meters over 2.5. This is the adjacent side, and this will be the hot ka, Okatawa. So this will be the unit that we'll be using to find the summation of forces on the x-axis. So let's copy this and write it 3 meters over 3.354 meters is FAC plus 2 meters over 2.5 FAB equals to 0. So notice that we already have the value acting on the FAB force acting from point A to point C. So we'll just plug it in, 100 kilonewtons. And to simplify, we have an amount of 178.9 kilonewtons. So now we have the value for both forces acting on the springs from point A to C and from point A to B. And just then we use another formula since we already have the complete information that we have So let's go back to the weight problem that we have here. Since we since there's no mass given, but given that we have to multiply it by the force of gravity, which is 9.81, so this will be MD 9.81 meters per second squared. So, minus MD multiplied by 9.81 meters per second squared plus we have here, I have to indicate first the forces acting on the y-axis from both point A to point B, point A to point C, from point A to point C, and from point A to point B. So we have here for the FAB, FAC, we have 1.5 over 3.354. This would be your adjacent. Where is adjacent? Because you have to be using the opposite. You should be using the saw, right? And for the FAB, we have this one, 200. It will be 1.5 over 2.5. We'll just go with the solution. So for point AC, it's going to be FAC. But before moving on, we have already solved for the forces for FAC. We're just going to use these numbers and plug it into our formula. That would mean it would be 100.178.9 kilonewton. This is 2 multiplied by 1.5 over 3.354 plus FAB. But we also have a value for FAB, this is 200 kilonewtons. So FAB is 200 kilonewtons multiplied by 1.5 over 2.5 is equals to 0. This is our longest formula that we have here. Solution. And to plug it in to your calculator, but we still have to find for our MD. But we end up with a total of 20.39 kilograms. Multiply it again by another kilogram over m over meters per second. Third, or round up to 20.4. Four, seven, three, three, six. It will result to 2.4 megagrams. The total amount will be 3,400 kilos. One, two, three. And that is all.